We are going to start today with relative velocity. This is one of the most important topics in physics, particularly when it comes to kinematics. So, relative velocity. First, let me tell you what I mean by relative velocity. I'll take up a simple example. Suppose here we have a car going with 25 meters per second. That's a huge speed, of course, and then we have another car which is going in the same direction with 40 meters per second, and we have another car which is going in the opposite direction with, let us say, 40 meters per second. There is an observer in this car. Now the problem of relative velocity is we have to find the velocities as seen by the observer. Here the observer is traveling in a car with a speed of 25 meters per second, and there are two other cars which are going with 40 meters per second, one in the same direction as the observer and the other in the opposite direction. So how do we calculate the velocity of this car as seen by this observer, and similarly velocity of this car as seen by this observer? All we have to do is, first we must bring the observer to rest. How do we bring the observer to rest? Whatever is his velocity, add negative of that velocity, add negative 25 meters per second to bring the observer to rest, because we want velocities as seen by the observer. So the observer imagines himself to be at rest and sees the velocities of all other bodies. So first step is bringing the observer to rest by adding a negative velocity. You add this negative velocity to every other object in the universe. Even to this car you add 25 meters per second negative velocity. Even to this car you add that 25 meters per second negative velocity. Suppose there is a tree which is stationary. You would add that 25 meters per second negative velocity to the tree also. So in effect, what is it that we are seeing? We see the observer at rest because you added a negative 25. Now the tree starts moving in the opposite direction as seen by the observer. This is normally what we see. When we are going in a car, we see the outside objects going backward. So the tree here is going in the opposite direction with 25 meters per second. Now see the speed of this car, 40 ahead, 25 backwards. So the net would be 15 in the forward direction. So 15 meters per second in the forward direction. And if the same observer would see this car, the speed of this car would be 65 meters per second. So all we have to do in relative velocity is add negative velocity of the observer. How do I formally write this in terms of an equation? For example, if you have an observer A going with a velocity VA, when I say going with a velocity VA, it is with respect to ground. If you have an observer B going with velocity VB, then velocity of B with respect to A as seen by A. How do we get the velocity of B as seen by A? We must add negative velocity of A to all the objects, to himself also, to all the objects. So you add negative of VA to VB. Add negative of VA. So it becomes VB minus VA. So you see that I read this as velocity of B with respect to A. In between I add the word with respect to. Velocity of B as seen by A is simply velocity of B minus velocity of A. Okay? So the concept is very simple. Now the application of this concept, it can be applied to many different scenarios. So we will start one by one discussing these scenarios. We have three types of scenarios where this relative velocity will be applicable. So the first one which I want to discuss is the case where there are two perpendicular roads which are intersecting at that point, and here there is a person A who is moving with a velocity of 4 km/h, and his distance from O is 3 kilometers. And on this road, there is another person B who is moving with 3 km/h, and his distance from O is 4 kilometers. Now, both are moving in their respective directions towards O, and we have to find the closest distance of approach between these persons. So, B is going this way, A is going that way. Now, they are going with different speeds. So, at some moment, if you see my hands, somewhere the distance between them is closer, after which it again becomes far. So, we have to find that distance where both these persons are close to each other. This is our problem. Now, this can be done in a variety of ways. I will discuss two methods. One is the normal logical method where you don't use relative velocity. The other is by using this concept of relative velocity. So, let us see the first scenario where we don't use relative velocity concept and solve this problem. Let us say after t hours, they are close to each other. So, A traveled for t hours, he is somewhere, B also traveled for t hours, he is somewhere else. Let us say at that moment, the separation between them is closest. So, in t hours, A would have traveled a distance of 4t. So, he would have come, let us say, up till here. This distance is 4t. After all, he is traveling with 4 km/h. In t hours, he would have traveled 4t kilometers. B would have traveled 3t kilometers. So, B would be there, 3t. So, A is here, B is there. This is the current separation between them. Can we get that? Can we get that current separation? It's very simple. From 3, if you subtract 4t, this will be 3 minus 4t. And from 4, if you subtract 3t, it will be 4 minus 3t. And we know the lengths of these two sides, we can get the separation by using Pythagoras theorem. So, the separation, which I call as delta, will be under root of 4 minus 3t whole square plus 3 minus 4t whole square. 4 minus 3t whole square plus 3 minus 4t whole square. That is the separation between them. This separation has to be minimum, and here we will use calculus. So, if you draw a graph between this delta and t, the graph might look like something like that. This is graph between delta and t. So, you see, at certain time, delta has minimum value. At that moment, if you draw a tangent, slope of the tangent will be 0. In other words, derivative of delta with respect to time has to be 0 at that moment. So, I have to differentiate delta with respect to time, equate it to 0. This will give me the time at which the separation is minimum. So, let us do that. If I do take derivative of delta with respect to time, I get 1 by 2 root 4 minus 3t whole square plus 3 minus 4t whole square into derivative of the inner thing by chain rule. So, 2 into 4 minus 3t into minus 3 plus 2 into 3 minus 4t into minus 4, and this has to be 0. Why this has to be 0? Because when the separation is minimum, at that time slope is 0. Slope is given by derivative of this y coordinate, which is delta, with x coordinate, which is time. So, derivative of delta with respect to time is to be equated to 0. And if I solve this, let me solve it here. If I solve this, what do I get? First of all, this numerator is equal to 0, denominator goes to the other side. So, we just have to equate the numerator to 0, and then we get 4 minus 3t into minus 3 plus 3 minus 4t into minus 4 is 0. So, if I simplify this, minus 12 plus 90 minus 12 plus 16t is 0, right? So, from here I get t. T is given by 24 by 25 hours. That is the time at which the separation between these two particles is minimum. I can put this time in this expression and get the minimum separation. See, this equation is giving you a relation between separation and time. So if I substitute this time here, I get the separation at which I get the separation which is minimum. So all I have to do is put this time in this expression. So that would give me the minimum delta, which I will do it here, delta minimum as root of 4 minus 3 into 24 by 25 square plus 3 minus 4 into 24 by 25 square. So if I simplify that, that would turn out to be 7 by 5, I believe, kilometers. So you can check the simplification. It's going to be 7 by 5 kilometers. This is one way to do this problem. What's the other way to do this problem? In fact, we have to use the relative velocity approach. Up till now, I haven't used this concept and I just solved the problem using the traditional calculus approach. But let's do this using relative velocity concept. And in fact, that solution might be a bit simpler. So let's see how to do it using relative velocity. I'm going to erase this situation. Okay, let's redraw the situation again. So distance of B from O is 4 kilometers. Distance of A from O is 3 kilometers. A is going with 4, B is going with 3. Let us work this problem in the frame of A. That means we assume A to be at rest and every other object is moving with some velocity as seen by A. How do we do that? First we must bring A to rest. How? By adding a negative velocity of 4 km per hour to A. If I add a negative 4 to an already existing 4, A will be at rest. But this negative velocity is to be added to every object in the universe, even the roads and the person B. So I add this negative 4 to B also. So effectively now A is at rest and B is now not moving with 3. He is moving with the resultant of 3 and 4, which is 5, because both are perpendicular. So I will show it this way. B's velocity is given by 5 km per hour. Originally he was having 3 km per hour. You added negative 4, the negative velocity of A. Why? Because you want it with respect to A, and you see B going with this speed. You can extend this. This is the direction in which he is going. That is the direction in which he is going. And we can even calculate the angle with the horizontal at which he is going. That angle is given by, if I call it phi, tan phi is given by opposite by adjacent. This is a vector diagram. I am drawing a diagram with vectors. Opposite by adjacent, 3 by 4. So I can say phi is 37 degrees. Tan 37 degrees is 3 by 4. Tan 53 is 4 by 3. These are magic angles for which you get the Pythagorean triplet without any number being irrational. 3 is rational, 4 is rational, 5 is rational. Okay, now we will also join A and B. We will also join A and B. This length right now is given by 5 kilometers. Why is it 5 kilometers? You can check that. 4 square plus 3 square is 5 square. And what angle does this line make with horizontal? The line joining A and B, what angle does this make with the horizontal? Let us calculate that. This angle is nothing but that angle. So I call it theta. And we have tan theta from the same diagram as 4 by 3, which is nothing but 53 degrees. So I did nothing here except for some geometry. First I brought A to rest by adding negative velocity of A. I added that negative velocity to every object in the universe, including B. And I saw the net velocity of B is now 5 kilometers per hour. I took the resultant of 3 and 4. and this velocity is making an angle of 37 with horizontal. Line joining A and B is making 53 with horizontal. So velocity is making 37 with horizontal. Line joining A and B is making 53 with horizontal. Now this is the direction in which B is traveling according to A as observed by A. You see B's distance from A is now getting closer, and after which it is increasing again. So at some point the distance between A and B is minimum. That is when I draw a perpendicular. So when B is here, this is the minimum distance between A and B. I call that distance as D. So our aim is to calculate this D. Simple. This is a right triangle. If you want me to name it, I will name this point as P. So triangle BAP is a right angle triangle. In fact, I know this angle. I can know that angle. How? This total angle, which is 53, minus only this angle, phi, which is 37. So this is 53 degrees minus 37 degrees. That is that angle. So now it's very simple. I just have to calculate this D. I have this triangle APB, which is right angled. So sine of 53 minus 37 is D by 5. Sine theta is opposite by hypotenuse. So sine of 53 degrees minus 37 degrees is given by opposite by hypotenuse, which is D by 5. My suggestion is do not simplify this. You just expand it as it is because it's easy. We know the values of sine 53 and cos 53 and sine 37 and cos 37. So we have sine 53 degrees cos 37 degrees minus cos 53 sine 37 is D by 5. Sine 53 is 4 by 5. So is cos 37. That's also 4 by 5. Cos 53 is 3 by 5. Sine 37 is 3 by 5. Should be D by 5. 4 square is 16. Minus 9 is 7. 7 by 25 is D by 5. Which implies D is 7 by 5. This is precisely the answer that we got in the previous method. So you see, using the relative velocity, there was a bit of geometry, but then the solution is quite simple. There is only one step solution. There is no calculus, no differentiation, nothing. So generally when you take up this topic, at that time you are not equipped with calculus. So this method would be more logical than the so-called calculus approach. I could have done something else here. Instead of taking everything in the frame of A, I can do the problem in the frame of B. So first bring B to rest by adding a negative velocity. Add that negative velocity to A to every object. Then construct the diagram and calculate using the geometry. Now this is one type of problem that we expect in relative velocity. There are two more problems. One what I call as river and boat problem, and the other what I call as rain and umbrella problem. These are the two categories which we have to discuss yet. So let's go to first the so-called river and boat problem. I will discuss what is the problem there, what we have to solve.